Now, does anyone know what a guy wire is?
I know. It's a wire that supports a vertical structure like an electric pole or antenna.
Very good. Let's see some examples.
But ma'am, how can a piece of wire support an electric post?
Come here and I'll show you. Now, suppose this is an electric post supported by a guy wire. Now, if the wind is blowing this way, in what direction will the pole fall?
It'll fall this way. I knew it won't hold it up.
Yes, but what if the wind blew in the opposite direction?
It'll fall this way. It won't fall. Oh, I see. So, the more guy wires you have, the less chance a pole like this will topple over.
That's right. Now, while you're up here, I want you to measure the length of the guy wire and the distance from the base of the pole to the point where the guy wire is attached to the ground.
Let's see. The guy wire is 8 inches. And the distance from the base of the pole to the point where the guy wire is attached to the ground is 5 inches.
Thanks, Jan. Now, class, is the pole perpendicular to the ground?
Yes!
Okay then, you should then be able to find the height of the pole up to the point where the guy wire is attached.
How?
I know. The guy wire, the pole, and the ground form a right triangle.
Oh, I see it. So what we have are the legs of one leg and the hypotenuse of the right triangle.
So, can you find the length of the other leg?
I'll try. Here's the pole and the guy wire. The guy wire is 8 inches and the distance from the base of the pole to the point where the guy wire is attached to the ground is 5 inches. We're looking for this height here, so let that be x. Now, based on the Pythagorean Theorem, the sum of the squares of the legs of the right triangle is equal to the square of the hypotenuse. Therefore, x squared plus 5 squared is equal to 8 squared. 5 squared is 25 and 8 squared is 64. Transposing 25, we end up to x squared is equal to 39. The principal square root of 39 is approximately 6.2. Therefore, x should be approximately 6.2 inches.
Good job, Lisbeth. Can someone come over and verify the work of Lisbeth?
I'll do it. She's right. It is approximately 6.2 inches.
As with any theorem, Pythagoras' theorem requires proof.
Ma'am, haven't we proved it already with all those triangles?
Well, we've only proved it for some right triangles and not all.
Oh!
Anyway, this particular proof is rather simple. Get your scissors, rulers, and scotch tapes ready. Okay, what we have are two squares. Suppose the smaller has a side measuring A units and the larger has a side measuring B units. What are the areas of the two squares?
Ma'am, the smaller one will be A squared and the larger one will be B squared.
Very good. Now here's the problem. Can you form another square out of these two squares? Let the square that will be formed be of some side C. As such, we want A squared plus b squared equals c squared. I'll give you a clue. Attach a squared to b squared like so before you start.
Aha! I've got it!
Can you show us how?
What I did was cut out two right triangles whose legs are A and B here and here. Once cut, you can rearrange all three figures to form another square like this.
Brilliant!
But ma'am, how does this show that the square of the hypotenuse is equal to the sum of the squares of the legs of a right triangle?
Well, the square we've just formed has one side that is exactly equal to the hypotenuse of a right triangle with legs A and B.
Really?
Really? Here, these should help. I have here a squared and b squared before they were cut up. I'll place a squared here and b squared here.
Oh wow! The square we formed out of a squared and b squared is as wide as the hypotenuse.
This proof is very old. It is attributed to an Arabian mathematician named Thabit ibn Qurra. Can you think of another way to prove Pythagoras' theorem?
I have an idea!
Could you show us this idea of yours?
Well, we can start with the right triangle with legs A and B and with hypotenuse C. We can form three squares, A squared, B squared, and C squared out of these, and then try to break down C squared such that we will form two squares, A squared and B squared.
That's a great idea. Fortunately, I have three such squares like these. Now, try to dissect the largest square, c squared, such that it will form two squares exactly like a squared and b squared.
I think we've got it, ma'am!
Alright then, show us how you did it.
Okay, I'll do it then. I first cut out a right triangle out of c squared here and place it here. Note that the right triangle I cut out is the same as the original right triangle. I then cut up the reconfigured c squared into two parallelograms. This parallelogram here has the same area as b squared, while this other parallelogram has the same area as a squared.
You did great, Lisbeth, but can you show us that indeed they have the same areas?
Sorry ma'am, I haven't gone as far as that.
Ma'am, I have!
Okay then, please continue where Lisbeth left off.
Notice that I can cut up the larger parallelogram like so and then move this piece here and we have b squared.
Now how about the other parallelogram?
I'll do it. I can cut the parallelogram here and move this piece here. Now, I trim off the excess which fits right here.
Good work, class! This particular proof was published by a mathematician named Gardner. Okay, so far we've gone through two proofs of the Pythagorean Theorem.
Ma'am, do you mean there's more?
Yes, but we won't go through all of them. Let's just try one more published by Gardner. I'm handing out one square per person. Let one side be of length a plus b. So, what is the area of the square I just gave you?
It's quantity a plus b squared.
That's right. I'll allow you to determine the lengths of a and b. But in order for us to generalize, make sure a is not equal to b. For example, on my square, this will be a and this will be b. I'll mark out a and b in all sides like so. And then, construct right triangles with A and B as legs. Of course, the hypotenuse of each right triangle will be
C!
Of course! Now, this will result in an inscribed square which has an area of?
C squared.
That's correct.
Shall we cut these out, ma'am?
No need. We all know how to find the area of a square and triangle, right?
Yes!
So, can someone express the area of this large square in terms of the area of its components?
I know. The large square has an area of quantity a plus b squared, which is equal to the area of the inscribed square, which is c squared, plus the sum of the areas of the right triangles.
And what is the area of one of these right triangles?
It's 1/2 AB, and since there are 4 of them, the total area of all these triangles is 4 times 1/2 AB.
So far, so good. What do you think we should do next?
I have no idea.
I have an idea.
Go ahead.
We can expand quantity a plus b squared into a squared plus 2ab plus b squared and simplify 4 times 1/2 ab into 2ab. 2ab cancels out, leaving us with a squared plus b squared equals c squared.
The two of you did an excellent job.
We certainly had an interesting math lesson today, didn't we?
Yes, we learned about the Pythagorean Theorem.
I can't imagine it was that old.
I know, we even proved it several times in class.
Yes, first we were given the task of forming a square out of 2 different squares, a squared and b squared. I was surprised that the new square, c squared, side c, turned out to be the hypotenuse of a right triangle whose legs are the sides of the original square a and b.
And then, we reversed the process. We assumed that C is the hypotenuse in a right triangle whose legs are A and B. We then managed to form 2 squares, A squared and B squared, out of C squared.